Tonight's fun. I have a computing devices company of Canada, SDA 103 signal distortion analyzer. So this is a device that can be used to analyze signal distortion on a serial line. So it's got a loop input here, which accepts a high voltage, well, actually accepts low current, 20 milliamp current loop, 40, 60 milliamp current loop, and or a polar voltage. Anyway, you plug it in, you set your bits per byte there, baud rate here, and it shows distortion. I guess I should show it working before I get to the next step. Hang on. Okay, so crammed in here, I have the SDA 103. This is a TMG 303, a test message generator, and a HAL Communications ST6, which I'm using as a loop power supply. Now I have the TMG 303 connected to this lovely little patch panel dealie here, which has a few different ports. These are set that when I pull the plug out, they'll close the loop, because this is a current loop, so these all need to be in series. The input doesn't have the switch contacts. And then these two are for this style jack here, whereas this is that style. So these have tip ring and sleeve. This just has tip and sleeve. These are great for shocking yourself, because on a teletype loop, that means there's going to be voltage there. So I just have to be careful. Anyway, let me plug these in. Okay, bits are plugged in. So I have the TMG connected through the tip and ring, because it's the only jack it has, or the SDA. The TMG has both a 310 and a 347, so that's a 310. The other one's a 347. Oh, that's a 310. The other one's a 347. I'm using a 310 because I like them more and I have more of them. All right. So everything's connected in series with the power supply, so I can turn the supply on, turn that thing on, turn that thing on. And I know that if I set the baud rate setting to 2, that's 74.2 baud. Let's turn this. I'll shock myself on it. Okay. Let me just get the switches set. I'll be right back. This is set for auto character length, which it didn't like. I just had to, this is a momentary, so I just push it down. And so I have set the test message generator. It has a distortion setting. Oops, doesn't mean anything on here. So I've set it to mark bias 15%, and I have this down here set me to show average bias, and it's showing 15%. So now if I turn this, that's 20, 25, 30, 35, 40, 45. And then I can also, so you can see, I don't know why it's vacillating between mark and space. It shouldn't. What am I set to? And this thing is kind of touchy. 14%, 20%. I think it, I don't know if it needs to warm up. It shouldn't. They're crystal controlled. So I'm on 20, 25, space. It's being a little temperamental. I should be able to set this to mark bias, and mark will come on. We'll go to space bias, or sorry, mark. That's mark bias, but where's space bias? I wonder if there's a Sketchers wood connection here. Space mark. All right, so that's what this thing does. So why is this on the bench? Here's the list of baud rate settings. This is for this switch here. There's 12 of them. And so 50 baud, what is that? I can't remember which standard that is. But 74.2 is 100 words per minute. And then there's the usual computer ones, 110, 150, 300, 600, 1200. Oh, but 1800, 24, 48, 96. So there's two oddballs there to me, which is 134.5 and 1800. Anyway, what I'm missing is 45.45, which is what a teletype machine wants. So I noticed that the test message generator was changed in 1977 to support, in addition to 56.9, it was changed to add 45.5 baud. So that got me thinking that I should be able to modify this one to do 45.45 baud. So let's take a look inside. This is how you get in. That's it. One screw. We're in. So it's oh, you know, I should do yeah, I should. I'm just gonna check those caps. Be right back. We're all good. They're all bled down. So that's the AC power supply unit right there. It's just a linear power supply. How can I position this? I don't want to mash the wires. And this is it's a card cage. It's actually really nicely built. I don't know what that transformer is for. I didn't realize it had another transformer hiding in there. 2 voltages. So that is a good old-fashioned filament voltage transformer, 6.3 volts. Made in Canada. But that one, it's another Hammond. Huh. Well, let's take a look. Here I've got the thing stood up. Yes, those are nixies. If you couldn't tell from the video earlier, the display is a nixie display. This is the board that we'll be exploring in this video, but this transformer's got me intrigued. So I'll yank that board out and see if I can see any markings on that. Nothing. Maybe I have to trace the... Oh, I know what that is. So I've seen that this in some other earlier or vintage-ish test electronics was to make something that was both 120 and 240 capable, rather than, I don't know why, rather than putting like a center tapped transformer, they would put a step down transformer in. So this, see all these jumpery guys here, and all the wires go to this transformer, which then goes to the input. This is a step down transformer. So to run this thing on 230 volts, you just move some jumpers around and it I don't know if it puts this transformer in line. I can't tell from how many taps it has. Yeah, something like that. I'm pretty sure that's what that is. That's just a 110, 240 step up or step down. Type C. See it there too. Anyway, let's set this aside for now. Beautifully built. Oh, I guess I should finish the... So that's power supply. And then there's 3 boards of logic, one of which I've extracted, the display board. I'm not sure what that one is. And then all the front panel stuff is all beautifully hand wired and tied. Very nicely made. There's a price tag on one of these. This one. Apparently, in 1977, it would have cost $1,200 to replace it. There's some fear-mongering there. Part of that was scare tactics to say, hey, employees of our company, don't lose this thing. Here's the board in question. So when I opened this up, there's another board with, actually all 3 boards have diode matrices on them. This one actually has 2. I don't know what that one is yet. But this one, given that it has 12 sections, And there's 12 baud settings. It seemed logical to be the baud rate selection. On here are a bunch of 74193s, which are counters. 1, 2, 3, 4. So that's 16 bits of counter. And I've got 1, 2, 3, 11 bits of... Anyway, I determined, and I will prove this to you in a second, that this is the divider programming, basically. So there's 2 clock crystals here, 11.52, and what's the other one? 11.97 megahertz, which is divided down a bunch of times to produce the clock signal. So here's me working out what all those work out to. So I put an X. Yeah, I put an X where there was a diode and where there wasn't. I just so happened to get it all in the right order. So that comes out to these different hex values, just converted to these numerical values, which when divided out, give the actual baud rate minus plus 1. Yeah. So this number, the megahertzage divided by this number plus 1 times some multiplication factor. There, these two. So for the 11.52 megahertz, 54,450, 11.97, 57,300. Was that right? Anyway, I worked it out. You can't tell from this. So 45.45 baud, the best divisor was using the 11.97 megahertz crystal divided by 1317, which gave me 45.444. I ran the numbers, all the other options, or using the other crystal, going up or down. The closest percentage-wise was this one. So that setting, 1316, these are the diode positions I need. There's that 134.5, and so I need to remove a couple and move one of them over. So, let's go back to this. There are 12 divider positions, and then there's this extra column which isn't labeled. So that one's labeled A, but this one isn't. And I figured out that is the crystal select. So when there's a diode present there, that means, have I got that right? Yes. To use the 11.97 megahertz crystal. So you see 110 and 134.5, use the 11.97 to get, because this is a distortion analyzer, you want it to be accurate. You want the clock to be fairly accurate. That's why they put these two values in. Right. So I need to figure out which one of these was the 134.5 baud, desolder a couple of the diodes, move one of them, and then test this thing out. All right, we're extracted. Where are they? There's the 3 diodes I pulled out. Those have there, and there. Those black marks are the Sharpie I used to mark the point where the diodes are coming out. And so now I need to poke one back in. And we're in. There it is. Just gotta clean up some flux residue on the back on that. And put this thing together and test it. So here's my plan of attack. I found the counter that's attached to the most significant bits up here. Are these the most significant bits? Shoot. Look. Pin 1 is on this end. Pin 1. Oh, pin 1's over here now. How about this one? Oh, it's on this end. Oh, that one's pointing. Nothing is oriented the same way. What a mess. Holy cow. Oh, the carry outputs of one of these counters, this one, goes to a JK flip-flop, which then goes to an output pin. So I'm going to pick up on that. I just need some reference of the divided clock so I can check to make sure with a frequency counter that I'm where I need to be. So I have written on my table here 10 top. So that's this connector, the top. Anyway. So I've just stuffed a wire into 1, 2, 3, 4, 5, 6, 7, 8, 10 top bottom connector into that pin, which I think should expose some divided out clock, and it bottomed out with that. I think that'll give me good enough connection. All right, I'll instrument it up. Black and red are the power rails here. I'll chase the wires out. The black ultimately ends up on chassis ground, so I know the ground isn't isolated, so I just pick the ground off of there. And, oh, I have to plug it in. All right, I think we have something working. So, let me just put that on marking. All right, so I poked and prodded all over this thing, and I couldn't find any signal that was consistent. It looks like when there's a signal on the loop, it triggers the counter to count down, which makes sense. So they would trigger the counter for the width of a bit period to measure something. It's not a continuous clock. So when you watch the scope, zoom in, I push a key, you can see something comes alive, but that's it. Otherwise that card is idle, there's no signal. If you look at the frequency counter, so I couldn't get a clean count out of it because even with a continuous signal, the gaps between the characters were causing gaps in the signal up here. Let me. All right. So, see those gaps in the trace there? Those are the characters. So if I zoom in on this, I can see a good clock. I can count on the screen and measure the frequency that way, which I did, and I checked it, and it looks close, but it's hard to tell on this old thing. But then I realized a good empirical test would be to fire up the test message generator and set the bias or set the distortion and then see what that thing shows. You know what I mean? I'm just checking where I'm at. One end. I'm not sure why it's not showing up. Alright, so it's upside down, forgive me. There's the switch set to 20, 25, 30, 35, and I see the teletype still chugging along at 40, 45, that's as high as it goes. And, oh, I'm totally out of beans. That thing is still, yeah, it's still typing something. Now I'll crank that back down to 0. There we go. The other thing to do. So now I figured out why the mark and space lights weren't working properly. Let me zoom in on this for you. And it's because I had the test message generator set to the wrong, I had set to ASCII. And some fiddling around I was doing. So now I can switch this to space, or mark, space, mark. So I'm flipping this switch here. And that's set to 10% distortion. That's set to 5, space. So that looks like it works. It's giving the right output. yeah. About the loop so I can hear myself think. So that pin that I picked coming off of that JK flip-flop was the only usable signal I could find. It turned out it was a good wild-ass guess. So if I change the baud rate selector here and I look at the screen, you can see that the higher the baud rate goes, the higher the frequency of that signal. But you can also see how it's blipping out. So there's 4. So that's my new 45.45. There's 110, which is right below it. And then below that is 74.2. There's 50. So if we look at 50, 50 is nice because it fits the divisions on the oscilloscope quite nicely, not surprisingly. Yeah, you can see 45.45 is just a bit slower. Thinking about this a little more, I get 1 cycle per baud. Per baud. Yeah. So, or per 10 baud. 10, 20, 30, 40, 50 baud. I change that to, what is that? 110. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, and then a bit. I don't know where the bit comes from. I don't feel like counting anything bigger, but let's go number 4, which is my 45.45, and I get 1, 2, 1, 10, 20, 30, 40, and a half-ish. So, yeah, looks like it's working right. My frequency counter just can't handle that weird triggering situation. If only I had a piece of equipment that could. There you go. That's how you convert a computing devices company of Canada, STA 103, to have a 45.45 baud. So I need to print in a little overlay label and stick it on there, and that's good to go. And then I have one more of these to do, but you probably don't want to watch me do that because this is painful enough. Thanks for watching.